So we have defined it as alpha plus j beta. So where alpha, you can say it is nothing but your attenuation constant, and beta is nothing but your phase constant. So in the previous class, I have already told you the assignment also, I guess. So after taking the square on both the sides, and if you compare the real part and imaginary part, you will get the value of alpha is something like this. So have you done this exercise? You can reply. Have you done this exercise or not? So, but I think nobody has posted in WhatsApp group, I guess. Okay, but anybody done completely? Have you got the same equations or you got the different ones? So what about others then? I think anyhow, by the next class, at least you try to do that, because it's just only a practice for you. It's not something like it is not related to your subject. So you should consider that. So by practicing that, you will feel comfortable with the subject. Okay. The only thing was my suggestion was whenever I say any assignment, try to take it in a challenging way, because that actually makes you to feel very comfortable with the subject. Or else what actually you may think was it is still looks to be more difficult part for you. So to feel comfortable, whatever the assignment I will say, you try to do that. Okay. Anyhow, the attenuation constant, if you see the units of that, so have expressed in the last unit, that is Napier per meter. And the phase constant, we have defined it as 2 pi by lambda, and it is in the order of radians per meter, right? So we have discussed the propagation constant. Then we have seen the different concept here, that is the loss tangent. Okay. So what if you see the equations of alpha and beta? So there is a specific term called sigma by omega epsilon. So that particular term is basically said to be the loss tangent. So the loss tangent is nothing but the ratio of sigma divided by omega epsilon. If you see the specific significance of the loss tangent, suppose when I ask you what do you mean by perfect conductor? So everybody say the perfect conductor is having conductivity equal to infinity. Similarly, when I ask what do you mean by a perfect dielectric, your answer will be sigma is equal to 0. So till now, whatever you have studied in your networks, you have defined the type of medium by considering only the conductivity in picture. But actually, if you see in the reality, all the mediums has been classified not only based upon the conductivity, but also the permittivity and the operating frequency. So I will tell a simple example. If you are considering about a conductors, the conductors is a good medium for the propagation of low frequency signals. You go to the high frequency signals, the conductors is not a good choice. You cannot transmit a high frequency signal through a conductive mediums. So there will be so many losses will be there. So what I mean to say was the frequency of operation is also one of the significant parameter in order to define whether that wave is propagating in that medium or not. So all the mediums has been characterized based upon the loss tangent. So you can make a note of that. So suppose when I say a good conductor, the loss tangent will be much higher than 1. Of course, suppose in your exam, if they say it is an ideal conductor or a perfect conductor. For an ideal conductor, your conductivity is equal to infinity. So which means that your loss tangent is also infinity. And similarly, if it is a good dielectric, the loss tangent will be much lesser than 1. Suppose in the question if they ask if it is an ideal dielectric, you should consider your sigma is equal to 0. So which means that your loss tangent is also becomes to 0. And then there is one more important thing, it is there. When anybody say it's a lossless medium, can you give an example of the lossless medium so that you can understand it better? You just give me some examples of the lossless medium, which means when I send the electromagnetic waves in that medium, there should not be any losses, which means your amplitude is going to be constant irrespective of the distance. Vacuum. So you can remember any lossless medium, when I say for electromagnetic waves, the conductivity of the medium must be equal to 0 for that medium. So when anybody say lossless medium in electromagnetic waves, the conductivity of the medium has to be equal to 0. You can see here, once I go to the derivation part, you can understand what is the reason why for the lossless medium, the conductivity has to be 0. So within a few minutes, you will come to know the answer for this. And next thing, what is the characteristics of the free space? So when you see the characteristics of free space, the conductivity is equal to 0 and your mu will be same as free space permeability and epsilon is equal to free space permittivity. So if you see, these are the general classifications how the different mediums are getting characterized. So if you have any questions, you can ask here. Fine, we'll go ahead. And the next concept is the phase velocity. So till now what we have seen now, when the wave propagates in any medium, we have seen how much attenuation is occurring, that is given by the alpha, and we have seen how the phase of the signal is varying with respect to time. Fine. Now in this next the thing is, suppose if we have a medium, let us say it is a free space only, and the wave is propagating something like this. The first question here is, if you transmit any electromagnetic wave, let us say you are transmitting in free space first, and suppose you transmit the same electromagnetic wave in the dielectric. What do you think is about the velocity? Do you think the velocity in the free space is same as the velocity in the dielectric? Will it be same or different? Different. Very good. So the type of wave is same. I was transmitting a transverse electromagnetic wave only, but the velocity of the wave is basically depends on the medium in which it is traveling. So suppose if it is traveling in free space, you can see that it travels with a velocity of light. Whereas if the same wave propagates in a dielectric medium, the velocity is slightly getting affected because of that relative permittivity. So that we will see. So as of now, you can see that the phase velocity is purely depends upon the medium in which the wave is traveling. So if you want to define the phase velocity, first let me write the equation for electric field and magnetic field of a uniform plane wave. So if you see the equations for electric field and magnetic field, we got something like this: E naught e power minus gamma z e power j omega t ax cap, and similarly h of z comma t is equal to h naught e power minus gamma z e power j omega t ay cap. So if you remember in the last class I have given the equations. So if you replace gamma is equal to alpha plus j beta, so what will happen? E power minus gamma z becomes e power minus alpha z into e power minus j beta z. Correct. So if you substitute this value in these two equations, so if you simplify that, you will get E naught e power minus alpha z e power j into omega t minus beta z ax cap. So h naught e power minus alpha z e power j omega t minus beta z ay cap. So I think I have given the explanation also why I was writing these equations in the form of this one. So if you look at these equations, it is very easy to identify which is the amplitude part and which is the phase part. Correct? So the first parameter represents how the amplitude of the signal varying, and the second part is how the phase is varying. So if we make a note of it here, the phase of the electromagnetic wave is varying with respect to time, varying with respect to distance. So till now, suppose if you are talking about in your networks, if you are talking about voltage and current, so there is a phase you have defined with respect to time. But as I mentioned in the last class, for all the electromagnetic waves is a function of time as well as the distance. As a result, the phase shift is also varying with respect to time and with respect to distance. So when you look at the definition of omega, so the value of omega, how will you define? So that is 2 pi by capital T. So this is a phase constant with respect to time, and the value of beta, you can define it as 2 pi by lambda. So if you look at the definition of omega and beta, I will just give it in a simple definition. So when you look at the definition of omega, when the signal travels for a time period of 1 capital T. So when the signal travels for a time duration of capital T, there is a total change in phase of 2 pi radians. So suppose if the signal is traveling like this, what is that omega rate represents? The moment once the signal traveled for a duration of 1 capital T, you can see here there is a change of 2 pi radians. So now can you answer me, if the signal travels for a duration of half of the time period, what will be the phase shift occurred? Pi, correct, right? So now I think you have understood. So omega is represents a phase constant with respect to time. So one time period of the signal, sorry, I should not call it as a signal, wave. So one time period of the wave should corresponding to a total phase shift of 2 pi radians for the wave. So that change in phase constant with respect to time, I can call it as omega. Similarly, what do you mean by beta now? When the signal is traveling, so you know that the wave is traveling in the space indefinitely. So when the wave is traveled for a distance of one wavelength, the signal undergone a phase of 2 pi radians. So that is nothing but your beta represents. Suppose if the signal travels for 1/4 of the wavelength, what will be the corresponding phase shift? You can answer me. When the signal travels for 1/4 of the wavelength, the corresponding change in the phase will be pi by 2. So that is what your beta represents, correct? Fine. So now you understood that the omega is the phase variation with respect to time and beta is the phase variation with respect to distance. So you are aware of all these two phase constant. Fine. Now, so you have defined omega is equal to 2 pi by T and beta is equal to 2 pi by lambda. Now, I want to define the velocity in any medium. So we know that the basic expression for the velocity is equal to distance by time. Right? Whatever the change in the distance divided by the change in time. So that is the basic definition for your velocity. Now, I get the same equation by considering one wavelength divided by one time period. Will you agree with me? Can I define the velocity in the medium by the ratio of one wavelength divided by one time period? Yes, because I can see distance is corresponding to lambda and the time corresponding to capital T. So in both lambda and T, the signal has undergone a shift of 2 pi radians. So if I want to define my velocity, I can define simply the ratio of lambda by T. So you just multiply with pi and divide with 2 pi. So what will happen here? So 2 pi by T is nothing but your omega. And you can see here lambda by 2 pi, you can call it as reciprocal of beta. So now my velocity can be easily defined by the ratio of omega and beta. So since omega and beta both are related to the phase of the signal, that I can name it as a phase velocity. So this is a very, very important equation. Even I can consider in the transmission lines, even if we go for the waveguides, I can apply the same formula. So the phase velocity of any electromagnetic wave in any medium is the ratio of omega by omega and beta. So since both are defined with respect to the phase, so I called the velocity as a phase velocity. So any questions here you can ask? And then next we will see the different parameter, that is the intrinsic impedance. So before straight away discussing about intrinsic impedance, I have a basic question in your network. Suppose if you are having a conductor and I want to know the resistance of this particular conductor. Okay, I don't know the specifications of this conductor. Fine, I don't know the length and I don't know the area of cross section and all. But in a practical way, I want to measure what will be the resistance of this. Can you tell me how to do? Anybody? I hope the question is clear for you. I want to measure the resistance of this conductor. I don't know the any dimensions of that conductor. How will you practically measure?
Sir, apply some voltage source across it and put a ammeter in series.
Very good. So if you want to measure the resistance of the conductor, you are applying some external voltage and finding how much current is passing through that. Fine. Then the ratio of voltage divided by current, you are calling it as resistance of that or impedance of that conductor. Fine. Very good. Now, similarly, if the electromagnetic waves are propagating in a medium, do you have any voltage and current? So do you have any voltages and currents existing in the medium? So when I talk about electromagnetic wave, do you have a voltages and current? Yes, sir. You can reply. So if I want to define the impedance of my medium, because the electromagnetic wave is propagating in that medium, there will not be any voltages and currents. So in other words, whatever we are talking about in electromagnetics, so the impedance of the medium I can define by the ratio of electric field by magnetic field. This equation holds good because when you're talking about medium, there is no voltage in the medium and there is no current because all these electromagnetic waves are generally propagating in a lossless medium. So whenever it is propagating in a lossless medium, your conductivity is zero. So which means that there is no concept of voltages and currents. So then the ratio of intrinsic impedance is defined by the ratio of how much electric field is existing in that medium divided by the magnetic field. So even you can, if you are having doubt, you can verify the units. So the unit of electric field will be volt per meter and the unit of magnetic field intensity will be ampere per meter. So if we say the ratio, that is the voltage by current, which is nothing but ohms. Fine. Now, if any electromagnetic waves are propagating in a certain medium, the impedance of the medium can be found by the ratio of electric field by magnetic field. So that is the definition for your intrinsic impedance. So the basic definition for intrinsic impedance is equal to E by H. Okay, let us assume that a uniform plane wave is propagating in a certain medium. So the equation for electric field and magnetic field, right? So that will be, you can say the magnitude at any instant of time. So electric field is E naught e power minus alpha z. Sorry, we'll take the original equation only. E power minus gamma z e power j omega t into ax cap, and h is equal to h naught e power minus gamma z e power j omega t into ay cap. So using your Faraday's law, I can apply this. So the curl of E equals to minus using your Faraday's law. This is the equation I got. And as I said in the previous class, wherever dou by dou t is there, you can replace with a j omega. So if you replace that, the curl of E is equal to minus j omega mu into, sorry, again there is a problem here. So curl of E is equal to mu into h. Now, when you are taking the curl of this particular vector, can you say what is the resultant direction? I want everybody to post what is the resultant direction of curl of E set to uniform plane. What will be the resultant direction of curl of E? Curl of E, is it lies in the which direction? Positive Z. No. See, first of all, del direction now. First, one by one you can answer. Del, the spatial variation for these two waves, if you are writing the del variation, is it lies in which direction? Good. So del is lies in the propagation direction, that is in the Z direction. And your electric field is there in which direction? So what is the resultant value then? Is it negative AY? AZ cross AX is positive AY, correct? So the resultant direction of curl of E, if you are seeing, that will be in the direction of AY cap. Okay. And when you are calculating the magnitude, you can see here, curl of E, if you are taking the magnitude, del is nothing but dou by dou Z itself. Because since the wave is propagating in the Z direction, you are having the rate of change also in the Z direction. So your dou by dou X and dou by dou Y will be 0. So I don't want to use the classical curl equation now, like a determinant format and all, because it is simply straightforward. My del lies in the direction of Z and electric field lies in the direction of X. So curl of E represents a vector. So the direction will be along Y direction and the magnitude will be straight away dou E by dou Z. Correct. So when you are writing the curl of E, the magnitude is dou E by dou Z and the resultant direction will be AY cap. Minus j omega mu into H. So you take the differentiation of this electric field with respect to Z. Forget about this direction now. This direction is already accounted here. So only you take this magnitude part and the differentiation with respect to Z. So what you are going to have? Minus gamma into E naught e power minus gamma Z e power j omega t into, so this is AY cap is equal to minus j omega mu, and the magnetic field intensity you can replace with the same formula. So the second equation we already having naught e power j omega t into y cap. So what happens right now? If you find the value of E H naught, so what is the value you are getting? So if you are taking the E naught by H naught, so your gamma will cancel. Sorry, gamma will not cancel. E power j omega t and e power minus gamma z both gets cancelled. and AY get cancelled, and this minus also get cancelled. So if you are taking E naught by H naught here, so there will be j omega mu is left over here and gamma is left over here. So the impedance can be defined as j omega mu divided by gamma. So this represents the impedance of your medium. So any questions here? So do you understood? This is just only the derivation I straight away give you this equation, but as I already mentioned, I don't want to give straight away any equation without telling the approach for that. Okay.
So,
Yeah.
how did you get the direction of del to be az cap?
No, in the last class you can see here, the wave is propagating in which direction here? In this case.
Okay, that exponential part.
Correct. So the wave is propagating in the z direction. So when the wave is propagating in the z direction, you have the amplitude variations along z only. Even you consider electric field or magnetic field, the electric field varying only in the z direction, right?
Yes, sir.
Yeah. So
Okay,
that is the
sir.
reason why del is in the z direction. Yes.
Okay.
So any other questions apart from that?
No, sir.
Yeah. So what is the final value we got? The intrinsic impedance is the ratio of electric field by the magnetic field at any instant of time. So in this case, I have considered a time t is equal to 0. So at time t is equal to 0, you are having the initial electric field and initial magnetic field. Or otherwise, you can define a time t is equal to t by 4. Similarly, magnetic field also at t equal to t by 4. So the ratio will always remain same as long as the time remains same. So that value we obtained it as j omega mu divided by gamma. And I think you can further simplify this. So we all know what is the propagation time. So root j omega mu into sigma plus j omega. So and hence resistance is defined by ratio of E by H. So if you simplify this further, you are going to get root over j omega mu by sigma plus j omega epsilon. So this defines the impedance of your medium. So any questions you have? So is the concepts clear? This one? Okay, if you are understood this concept, so let us try to answer for this question. So I have a particular region, I have a particular medium, and in which I was passing some electromagnetic waves. So in the first case, I have considered my electric field is 10 joules per meter, and the medium remains okay. And in the second case, so let us say the electric field strength has become 2 per meter. So compared to the first case and second case, what happens to the impedance of the medium? So when the electric field increases, the intrinsic impedance of the medium will change, or it will remain same. So you can answer now. So when I transmit an electromagnetic wave with a higher strength of electric field, does it have any influence on the impedance of the medium? So the question is simple. Increase, remains same, changes. So okay. So whoever is telling, somebody is saying it changes, right? So let us try to answer this question. So in the previous case, you already defined like, so you are having a conductor. So let us say you have applied a voltage of 10 volt. Okay. And you have applied a 20 volt afterwards. So when you apply 10 volt, whatever the resistance you get here, when you apply the 20 volt, will you get same or different? Same. So suppose when I say 10 volt, it may corresponding to 10 ampere. So the ratio of resistance, voltage by current, you are going to get 1 ohm. Fine. Now this time what will happen when I apply 20 volt? So when I apply 20 volt, the current will proportionately increase. Correct. But ultimately, what is the ratio here? 20 volt divided by 20 ampere, you are going to get a resistance same. So the point is here very simple. The voltage and current cannot influence the resistance of the conductor. In the same fashion, if you pass more electric field, it doesn't impact the impedance of the medium. If your electric field increases, proportionately your magnetic field also will increase. So making sure that the ratio of E by H is always maintains constant value. And in fact, the impedance of the medium pure depends based upon these constants, sigma, omega, and epsilon. So you got the problem? So the strength of the electromagnetic signal or waves cannot influence the impedance of the medium. Fine, good. So that's it. Now, if you see the major classifications, what we have done. So there are three parameters which we are analyzing when the wave is propagating in any medium. So the first parameter what we are analyzing is the propagation constant. So if we recollect once again what we have discussed, so that is nothing but alpha plus j beta, and this is nothing root j omega into sigma plus j omega epsilon. And the second one is the phase velocity, that is the ratio of omega by beta. And the third one is the intrinsic impedance. So that is root over j omega mu by sigma plus j omega epsilon. So these three are the parameters for analyzing the wave. So when the wave is traveling in any medium, you want to find out what is attenuation and how the, and the next thing, how will you analyze? Will be the velocity of the wave. And the next thing, what will be the impedance of this wave? So this will completely characterize whatever you want to analyze related to the electromagnetic wave propagation. Further in our discussion, we will see propagates in different free space electric centers. See what attenuation, velocity, and the impedance. So ultimately, it is basically depends upon these three equations only. So do you have any questions here in related to the three equations? You can ask me now. And will be not epsilon r. Only your sigma will be 0 and your mu and epsilon will be existing, right? And now you take some time, you know all the equations, right? So I have given all these equations. And what is your phase velocity? Omega by beta. And this impedance. So your gamma will be alpha plus j beta in turn. So one case I will do, the remaining mediums, you can do the same approach. Whatever the approach I was following here, the thing you can do for the different mediums. So first thing, when I see the propagation constant, you can substitute here. Your sigma will be 0 and mu will be not into mu r, and your sigma will be 0. And your epsilon will be epsilon naught epsilon r. So what is the value of gamma you are getting? So j omega into root mu naught epsilon naught into root mu r epsilon r. So this is basically equal to alpha plus j beta. Fine. So by comparing these two equations, can you tell me what is attenuation here? You can reply. Yeah, because it is purely a imaginary part. You can see here your real part is 0. Your alpha is 0. So when alpha is 0 means there is no attenuation exists in the case of a lossless medium. Now do you got the reason why I have characterized all the lossless medium by sigma is equal to 0? Suppose if you have a finite value of sigma, what will happen here? If you have a finite value of sigma, this term is going to be a complex number. So when you have a complex number, you will definitely have the value of alpha. Okay. So when I say a lossless medium, propagation constant has to be pure imaginary. So you should not have any real. So you cannot get any part whenever your sigma will be 0. That's what you have seen here. So I hope you got the answer now. For lossless medium, it should be real. So do you got the answer, everybody? You can reply here. If I to repeat, I can once again repeat. Okay, anyhow, fine. So in order to have a lossless medium, my alpha has to be equal to 0, which means that your gamma. So gamma becomes binary provided the first condition should be 0. Okay, that's what you have seen. So when you are 0 indefinitely, you can say that attenuation is 0. And by comparing value of beta, so what you will get? Omega root mu naught epsilon naught into root mu r epsilon r. So this is the value of your phase constant. And the next thing, what will be the phase velocity? So the phase velocity is the ratio of omega by beta. So when you are calculating omega by beta, you can see here 1 by root over mu naught epsilon naught into 1 by root over mu r into epsilon r. So if you see here, this is 1 by root over mu naught epsilon naught. You know the value of mu naught will be 4 pi into 10 power minus 7, and epsilon naught will be 1 by 36 pi into 10 power minus 9. So if you are calculating 1 by root over mu naught epsilon naught, this is nothing but your 3 into 10 power 8 meter per second. So this is same as your velocity of light. So just substitute mu naught and epsilon naught. You can verify whether you are getting 3 into 10 power 8 or not. Okay, so this term 1 by root over mu naught epsilon naught is basically said to be the velocity of light. So the phase velocity in a lossless medium is nothing but c divided by root mu r into epsilon r. So next thing is the impedance. So what is the impedance here? So the impedance is nothing but you can use the formula root over j omega mu naught mu r divided by j omega epsilon naught epsilon r. Your sigma will be 0. So that is equal to root mu naught by epsilon naught into root over mu r by epsilon r. So you can verify, you substitute the value of mu naught by epsilon naught. So the square root of mu naught by epsilon naught is equal to 125 ohms or the 377 ohms. So you can do that after substituting the value. So the impedance in a lossless medium is equal to 120 pi into root over mu r by epsilon r. So now you are able to define in a lossless medium what is the attenuation, what is the phase constant, and what is the velocity, and what is an impedance. So any questions in the approach that what I have followed here? So next consider the different medium. Next one. So next you consider the same thing, whatever the approach I have followed, you would consider the same thing. The medium is a free space now. So when the medium is free space, your conductivity is 0 and mu is equal to mu naught and epsilon is equal to epsilon naught. So do the same method. You tell me all the values, alpha, beta, and what is the phase velocity and what is the impedance. So take the time and tell me all these answers. 0 degrees, correct. Okay, we'll go to the next case then. So we see that wave propagation in ideal dielectrics. So when I say in ideal dielectrics, so in the last tangent, I forgot to give you one more definition. For an ideal dielectrics, your conductivity will be equal to 0 and your relative permeability is equal to 1. So your mu is equal to mu naught for all ideal dielectrics. So there you can correct it. When I told in the last tangent, I told only this point, your conductivity is 0. But for all ideal dielectrics, not only conductivity is 0, but your relative permeability is said to be 1. And of course, you are having epsilon value. That is epsilon naught into epsilon r. Okay, now you go ahead and quickly tell me what is the values you got. So once you are done with that, you can tell me now. Yes. So what is the definition I have given for the good conductors? So you should remember.
Sir, sigma by omega epsilon very greater than 1.
Very good, very good. Sigma by omega epsilon must be much higher than 1. You should not consider sigma equal to infinity. Okay. Sigma is infinity, we can consider if it is an ideal conductor. But I am not going to talk about ideal conductor. Okay. In reality, you don't have any ideal conductor. So I was always focusing my attention towards the good conductors. So in case of a good conductor, the last tangent is much higher than 1. Okay, this I will explain this part, what will happen attenuation and phase shift. So first let me start with the propagation constant. So as usual you have root over j omega mu sigma plus j omega epsilon. So take sigma common from the first term. So when you take sigma common, so first term will be 1 plus j omega epsilon divided by sigma. Okay, so since your last tangent is much higher than 1, your sigma by omega epsilon is very high, the reciprocal can be neglected. So let us say your sigma by omega epsilon is somewhere going to infinity. So the reciprocal of infinity can be approximated to 0. So the second term I can neglect it in a good conductors. So what will happen? The propagation constant is equal to root j into root over omega mu sigma. Fine. So what is the value of root j here? So when you want to write the value of root j, that is equal to, somebody is saying root j is equal to -1. It's hard to digest, but the actual fact is root -1 is equal to z. Isn't it? It's not root j equal to -1, it is root -1 is equal to j. I hope you got the difference. Fine. Yes. So when you want to write the value of root j, so it is j power 1 by 2. Correct. So j can be written as e power j pi by 2 whole power 1 by 2. Why? Because when you are seeing the value of j, when you are calculating any e power j theta, you can see here, e power j theta will be cos theta plus j sin theta. So suppose if you are calculating e power j pi by 2, what will happen? That will be cos pi by 2 plus j sin pi by 2. So cos pi by 2 is 0 plus j sin pi by 2 is j. So the value of j can be written as e power j pi by 2. So since j power 1 by 2 is there, so that will be e power j pi by 2 whole power 1 by 2. So what you are going to get? So root j is equal to e power j pi by 4. You can apply the same thing here. E power j theta is equal to cos theta plus j sin theta. So if you substitute that, you can say theta is equal to pi by 4 here. So here you will get cos pi by 4, sin pi by 4. Both are 1 by root 2. So the root j value can be written as 1 plus j by root 2. Okay. This is your very important point you have to remember. So hence the propagation constant can be defined as 1 plus j by root 2 into root omega mu sigma. So this is of the form your alpha plus j beta. So by comparing these two equations, what you will get? So your alpha value is same as beta value because your real part and imaginary part is same, is equal to root over omega mu sigma by 2. So you can slowly verify, no problem. You can see the value of alpha and beta remains same, and this is given by root over omega mu sigma by 2. Now you can focus here. So what happens to the attenuation now when the frequency increases? So when your frequency is high, your omega will be high. So the attenuation is going to be high. So what happens explicitly at low frequencies? As I mentioned, in a good conductors are best suitable only at the low frequencies. So because at low frequencies, your omega will be 0, your attenuation is going to become 0. So what will happen as the frequency increases? So the attenuation is also gradually increased when you are increasing the frequency. So till now, whatever the mediums we have studied is all are lossless. So what happens when you are going for the good conductors? As the frequency increases, the amount of attenuation is going to increase. And unfortunately, all our communication is happening in the high frequency. If we take satellite radar communication and all, those are all operated at gigahertz frequencies. So when you are operating at gigahertz, and if suppose if you are choosing a good conductor, your attenuation will be significantly high. So that is the reason why the conductors will not be preferred at high frequencies. So when I talk about electromagnetic wave propagation, our attention is fully towards the lossless mediums. We don't want any attenuation to be happen until and unless there are any reflections. Okay, you got the point here? So any question in propagation constant? So understood or not? Yeah. Then you don't find the phase velocity. I will tell the phase velocity later. Find the intrinsic impedance first. What will happen in case of a good conductor? What will be the intrinsic impedance? Root j omega mu by sigma plus j omega epsilon. So same thing, you can take sigma common from the denominator. So when you take sigma common from the denominator, you are going to have 1 plus j omega epsilon by sigma. So what will happen here? As the last tangent is much higher than 1, the second term is going to be 0. So you are going to have root j into root over omega mu by sigma. Again the same thing, root j can be replaced by 1 plus j by root 2 into root over omega mu by sigma. So when you are calculating the impedance of the good conductor, it's a complex number. So it's quite different than what we have seen before. So till now we have seen the impedance phase angle will be 0 and which is purely real. And this is the first time where the impedance of a good conductor becomes complex number. So if we separate the real part and imaginary part, you are going to get this root omega mu by 2 sigma plus j into root over omega mu by 2 sigma. So this is basically called your skin impedance. So this is called the skin impedance of the conductor, and the real part is called skin resistance, and the imaginary part is called skin reactance. So this is, I can say, Rs plus J into Xs. So Rs is the skin resistance and X will represent skin reactance. So in a short time, I will discuss about what is the skin effect called. Until as of now, you can see that the impedance of a good conductor is a complex quantity. Can you tell me what is the phase angle between your electric field and magnetic field in this case? So when you have a look at the equation, what is the phase angle between E and H? You can answer quickly. Why you are taking so much time now?
Sir, 45 degrees.
Correct. Correct. Because your skin resistance and reactance will be same, right? So suppose if you have a complex number x plus jy, so what will be the phase shift here? Tan inverse imaginary part by real part. So in this case, your imaginary part and real part both are same. So you are going to get a value tan inverse 1. So tan inverse 1 is equal to pi by 4. So it is plus 45, you can see here. So in a good conductor, your electric field is leading the magnetic field by 45 degrees. So which means that you can see here, this is your electric field and magnetic field is starting after some duration. So the phase angle, if you see between E and H here, this will be 45 degrees. So your electric field leads the magnetic field by an angle of 45 degrees because it is positive. So you got the point now? Any questions to discuss here? Yeah. Next we will see what is basically called the skin effect or the skin depth. So let us say the wave is entering from the free space and this is my conducting medium. So this is my free space and this is my conducting medium. So in this case, consider it is a good conductor. Now ideally speaking, in our boundary conditions what we have studied, when any signal incident on a conductor, everything will get reflected back. But that is an assumption by considering it as an ideal conductor. But what will happen when you have a good conductor? When you have a good conductor, the signal will penetrate into the conductor for a certain distance. Okay, suppose if you have a big conductor, inside the conductor, the signal can penetrate over a little bit of distance. So that distance is going to vary with the frequency. This is basically called the skin depth. So the skin depth is actually represents what is the penetration of the electromagnetic wave inside a good conductor. What is the distance it has traveled inside the conductor? That is what given by the skin depth. So there is a mathematical way of explaining it. So when you have any conducting medium, so what is the skin depth says? So suppose this is your conducting medium. So I had a very big conducting medium, something like this. So when the signal is incidenting here, let us say starting from here. So you may have a 100 volt per meter. So as I said, in case of a good conductor, the wave will travel for a certain distance. It will not immediately get reflected back. So how the skin depth is defined was, so it is the distance traveled by the wave such that the wave gets attenuated to 1 by E times of its initial electric field. So let me explain again. So on the interface, suppose you are having a 100 volt per meter. And now the signal is penetrating into the conductor for a distance of d. So when I say if the distance is equal to 1 skin depth, after traveling a distance of 1 skin depth, the electric field is attenuated by 1 by E times. So the skin depth represents distance traveled by the wave inside a conductor such that your electric field at that point becomes 1 by E times of your initial field. So here your initial field is 100 volt per meter. After traveling 1 skin depth, the strength of the signal has become 100 divided by E. So that is how your skin depth is defined. Is it clear? You can reply. Is the concept of skin depth clear?
Sir?
Yeah.
Sir, how to read that symbol of that skin depth?
It is also basically said to be delta only.
Okay.
It is said to be delta only. Correct.
Oh, okay, sir.
Yeah. So the ultimate definition was, what do you mean by skin depth? Was in a conductor, inside a conductor I was talking about, in a conducting medium, if the signal travels for 1 times skin depth, 1 times delta, I can call it as 1 times skin depth, the electric field becomes 1 by E times of initial field. Suppose before entering the conductor, if you have a 100 volt per meter strength of signal, once it enters the conductor and travels for a distance of 1 skin depth, the strength of the signal has become 100 divided by E. So that is a mathematical explanation. So it is sufficiently getting attenuated when it is traveled for 1 skin depth. So that is what it represents. So I will put it in a more elaborative way. So as you know that we have seen in the uniform plane wave, so the electric field is attenuated with a constant called e power minus alpha z. Right. So as per the skin depth is concerned, so when the signal travels for a distance of 1 skin depth, what happened? Your electric field has become 1 by E times of your initial electric field. So the skin depth is defined as the distance traveled by the wave inside a conducting medium such that your electric field at that point becomes 1 by E times of your initial electric field. So when your Z becomes 1 time delta, your E becomes 1 by E times of your E naught. So if you substitute that, so what you are going to get? So 1 by E times of E naught is equal to E naught e power minus alpha Z. So e power minus 1 is equal to e power minus alpha. Of course, your Z will be same as your delta. So base is equal. Now you can compare the powers. So when you compare the power, you are going to get alpha into delta is equal to 1. So this is a very, very important relation in a good conductor. So it is inversely proportional, you can see. Hence the skin depth is defined as 1 by alpha. Alpha is nothing but your attenuation constant. So we have seen in the previous slide, the attenuation constant is given by root over omega mu sigma by 2. So the reciprocal of attenuation constant is given by this. So root 2 by omega mu sigma. This is the expression for your skin depth. Now you can see here, as the frequency is high, the skin depth is less. So what is the meaning of that? So when the frequency is high, your skin depth is low. So when you pass any high frequency signal, it will not penetrate more into the conductor. Of course, it will penetrate for a small distance. That's it. So as the frequency is high, the penetration of the wave inside the conductor is going to be less. Similarly, as the frequency is low, your skin depth is more. Which means if you have a good conductor and if you have a low frequency signal, it can penetrate more deeper into the conductor. So whereas if you pass a high frequency signal, the penetration will be very less. So that is what your skin depth represents. So any questions here till now?